All right, sorry about that. The headset that I had on my stream box wasn't working, so I had to restart it. All right, so today I wanted to do some more work on this epoll file server. So I got an initial commit here with like a rough implementation, and I guess there's a lot of work to still be done. But off stream last night, I just had a lot of energy, and so I just like, okay, I'll just do some work on this epoll server. And if I do LT now, you can see there's a source directory. It has a bunch of different files in it now. So these are compiled into O files and then linked against the main C. And so the main C is like super minimal now. It does some argument parsing, converts those args into the adder info data structure array, and then I think it's technically a linked list, but it's implemented as an array, a linked list in a contiguous part of memory, I believe. I guess that's another thing I need to add it to do here. Does this need to be freed? Because it's generating this array. I didn't give it the array, so I'm kind of curious where I should free that. But I handed off to this function listen on adders. So it takes the adder info struct, listens on all those, and gives us back a epoll accept file descriptor. And then we have a pool that we start up of threads, and they'll be working on this epoll connection file descriptor. And then we go into this accept loop where we accept connections and put them onto the connection file descriptor for the pool to work on. So that's like the high level overview of that. Pretty simple. I was thinking about pulling this out maybe into like another function. Give me 1 second here. I need to disable locking on my stream machine. I always forget to do that on startup. Okay, there we go. Yeah, I was thinking about pulling this out into a super minimal thing. So like main in my mind, since you have to call it with this argc argv thing, it's really only useful to be called from like the actual program getting invoked via execve. And as a result, like it makes it to where you can't really like run this code multiple times and inside the same process. It also makes it to where it can't be invoked as a library. Not that either of those are use cases for us right now, but my general vibe is like pull everything out of the main except for argument parsing, environment parsing, like converting all your arguments and environment information into the information needed to drive your program, and then call into a library. You know, get it out of the main function, because you can't invoke the main function independent of running execve. I guess you technically could, but you'd have to construct an argc argv, which is a rather strange interface. I think for now though it's pretty minimal, so I'm just going to leave it as is. But yeah, that's where my mind is on that. I'm going to start a to-do list here. So to-do.md, and we're just going to do like a bunch of stuff here. We're going to say, hey, implement http 1.1 gets. What else? I think before that we're gonna want to do stuff like so use send file to actually send file data. So I was thinking, we would do the write operations. So we would read the data from the connection socket into our buffer for the HTTP header. Then we would then parse the HTTP header for the file. We would then open the file. We would then perform reads on the file and write them to the reads on a file cannot block. I guess technically they could block if it was like a virtual file system type thing. But for the most part, you can just like consider normal file IO and regular files on a normal file system. They're not going to block because they're going to be in the kernel's page buffer. We call it page table cache or whatever. Page cache? Is that the right term? Basically, like the kernel maintains a bunch of caching for file IO operations. So you don't actually have to hit the disk every time you want to do IO. I guess those things could block though, right? Like say the hard drive controller is just like, you do a read, it's not stored in the cache, it has to go to the hard drive controller. The hard drive controller is just like, hey, give me like, 800 milliseconds to perform this read because it's like a really slow hard drive. Then yeah, I mean, it's going to block. Read is a block, unless you have non-blocking mode enabled. Read is a blocking API, so yeah. One second, I have an alarm going off. Be right back. All right, sorry about that. So I had to take a quick call. All right, so what I'm gonna do is, right now I have like an echo server implemented. It's really like broken. It's not really a great echo server. And considering that I don't want this to be an echo server, I just had the echo ability there just to kind of demo the connections and everything. I think I'm just gonna like continue to use a very basic TCP read line model where it reads a line, then tries to open that file descriptor and does a send file for it. So I think that'll be probably our next step. Or move to basic file reading. Add basic file reading. And then we'll say use okay, so that's top of the list there. And since the kernel is like out of the, since the user space is out of the picture, it's like calling this kernel send file. It's saying, hey, you kernel, you handle the sending of the file. That means that there is no write side I have to worry about, which is really nice. So let's go ahead and do that. All right, so let's go under the worker because it's the guy that's doing all the work and all these to-dos here. So, this echo record, I'm gonna rename, obviously. So this will be request record, or yeah, rec record. I like that. These buffers, since it's more than just a buffer, it's a location in the buffer, and it's a mutex guarding the buffer. I don't really like calling this thing buffer. I also don't like statically allocating it because it's dependent on your process's U limit and R limit stuff. So let's find where this is referenced. So it's referenced obviously in the global and the handle event aggressively. And it's also handled over here where we init it. So I think what we can do is we extract out this init code. We'll call this records. And we're going to make this a pointer. So we're basically going to be doing this. So let's pull this stuff out here. And we're going to go up here and next to this memory here. So we're going to have a function here that we'll just call this thing init record. Maybe say record init. Record init. And in here, we'll just do a void here. We'll say, hey, give me the FD, which will be an integer. And we're going to use that FD to index into our records array, grabbing the mutex, initializing it to that, and then we'll do the same thing here. FD. And this is going to be, buff is actually a char star. Okay, so we also did some allocations down here. So down here, we did this allocation here. So let's pull that up into this function. So now we have our buff. We can PR and exit. That looks good to me. Buff size, that's another magic number. So we'll say what is the largest HTTP 1.1 header size? Set a hard limit on header size. Instead, it says server may impose limits on individual header field size, total header size, individual header field size, total header size, number of headers. If the request is too large, the server can return request header fields too large or bad request. 431. We'll add a to do here. If request header size exceeds buff size, make sure to respond with 431. We'll just say respond with 431. All right. So it's a little note for us in the future to handle that condition. Okay, so we initialize everything. So this is a record init. And then we want also void records init. And this thing is going to, using our limit, in C, read the current file descriptor limit. There we go, get our limit. Oops. For some reason, whenever I copy from ChatGPT, it doesn't do it. Okay, so we need this sys resource. See? I copied it like 100 times. Didn't want to copy it. Alright. So now we say, hey, I don't like the style, so I'm going to pull this thing out. Say, hey, get our limit, error, int, semicolon. And if I open up man to get our limit, it returns an integer. And if I look at return on success, they call it 0, on error -1 is return. Okay, so we need to check to see if error is equal to -1, in which case we need to exit with exit failure. No returns needed here. So once you have the R limit, then there's an R limit a cur and a max. So I'm going to run with cur because cur can only change up above its current value to the max level, and it can only do that within the program. Like, you can't reach into the program and monkey with these things. The program itself has to do these things. So since we are the program, we're not going to do those things. We're just say, hey, if you invoke this thing and you want to increase the file limit, you need to do it before you invoke the program. So we'll grab this limit, this guy here, and we're going to use that for a malloc call. So we're going to, oops. I actually want to calloc. Man calloc. I think it's a 3. So calloc allocates memory for an array of n elements. Oh, hey, what's up, man? So I tried to run the AI locally via the Llama cause of no GPU. The CPU go to 100% with around 200 watts of power. I've only run Llama on my MacBook, and that was like a couple of years ago, or a year ago. I forget how long ago it was. But yeah, definitely not a CPU workload. So today I'm working on building this epoll Fileserver. And I have most of the code already done for it. Or at least most of the architecture is established for it. We discussed this on a previous stream. And I got most of the code to match the architecture. So now what's remaining is basically adding the basic file reading using send file, and then implementing the HTTP 1.1. Epoll is a system call that allows you to monitor multiple file descriptors to see if they're ready to perform I/O. It's used in a lot of network programming. Go uses it a lot in its netpoller capability as part of the runtime. I think Nginx uses it as well. But it's like one of these system calls. It's Linux specific. It's similar to select and poll. We talked about those earlier when we were reading the Linux programming interface. But basically, it allows you to like monitor multiple file descriptors. So if you do a man to on epoll create, so this is how you create it. You just call epoll create. It gives you back a file descriptor. This size thing, you can give it a size. It's kind of like a argument that doesn't really mean anything anymore. Or you can give it flags. Once you have the epoll file descriptor, then you can use epoll CTL. Pass it the file descriptor, and then you can do these operations to add, modify, or delete other file descriptors from what they call the interest list, which is like a list of file descriptors that this epoll file descriptor is interested in monitoring for I/O events. Then once you're done with adding and removing file descriptors, you can then call epoll wait or epoll pwait, which basically allows you to say, hey, I'm going to put my thread to sleep and wake it up if there is I/O events available on these file descriptors that I'm interested in. And then tell me what file descriptors are available to perform I/O and what types of I/O they're able to perform. And then you can give it an optional timeout here. And then the pwait stuff is just for handling signals stuff. So if you look at the diagram here on the left, let me zoom in a little bit here. So the general idea is that we have one thread of execution, which is the main thread, that's going to be accepting connections, as many connections as it possibly can, on a pool of sockets that it has that's listening. And then once those connections are accepted, we need to have threads that are working on handling those connections. And so we put them all on this epoll file descriptor that's then shared between a bunch of worker threads. And these worker threads are waiting under epoll wait for new connections. As soon as a new connection comes up and it's able to do I/O, then it gets picked up by a worker thread. The worker thread then performs the I/O. It also has to take exclusive access to the file descriptor. So we have a mutex that's part of our data structure that allows us to take exclusive access to that file descriptors. Otherwise, all the other threads will kind of compete to to do the work for the file descriptor, and we don't want that. We want one thread to exclusively acquire the file descriptor, perform the I/O operations, and then release it. So once the worker thread gets exclusive access, it performs the reads, modifying the buffers, does the writes. If the I/O op would otherwise block, we put the file descriptor back into the interest list and remove the exclusive access. And then when the write fully completes, we zero out the state and return the socket file descriptor into read mode. This is going to be a little bit different because I'm going to be using this system call called send file, which is an optimization that allows you to just hand the file descriptor to the kernel and say, hey, you kernel, you do all the I/O. I'm done dealing with this. You do all the work. And so that allows us to move on to other tasks. It's kind of like an asynchronous I/O type feature because you're giving it the kernel a socket file descriptor, and you're giving it a regular file descriptor, and you're saying copy all the bytes from the regular file into the socket, and don't wait for the user space program to do all the copying. So they call it a zero copy IO, because you're not copying data from the kernel into the user space back into the kernel. There's none of that copying going on. So that's an optimization, just in minimizing copies. But also the fact that the kernel can perform the IO independent of waiting around for you, waiting around for the user space to actually do the work. It allows the user space to continue doing other work. And the goal here is that we want to get a file server that's capable of handling as many IO requests, as many concurrent get requests from concurrent connections as possible. Like I want to pass the C10K test basically. So that is where we're at on this guy. So let me go back here. I'm going to give myself a little bit more room here. Okay, so we were initializing the global array that is going to be used to store all the state for these connections. And I called it records because I couldn't really think of a better name for it. But it's basically an array of these structures. Every file descriptor gets one of these records. Let's see. So we go to records init. We read our limit for the current number of file descriptors, and then we need to do some allocation to we need to do an allocation to, and we don't need to free this, but we need to do an allocation to that global memory for the number of file descriptors that we have. So if we look at calloc is for arrays. So you can do a malloc n times size, which is what I normally would do, but the calloc I think also zeroes out the memory. So the calloc function allocates memory for an array of n elements of size bytes each, and returns a pointer to the allocated memory. The memory is set to 0, which is different from malloc. Malloc, the memory is uninitialized. If n or size is 0, then calloc returns a unique pointer value that can later be successfully passed to free. If the multiplication of n and size would result in an integer overflow, then calloc returns an error. By contrast, an integer overflow would not be detected in the following call to malloc, with the result that an incorrectly sized block of memory will be allocated. So that's another advantage that it has over malloc. So if we call calloc, you give it size n and then the size of each element. So our limit is going to be the number here. And actually, I'm going to assign into here integer. Actually, no, I want to find out what type this is. So this is our limit t, which is this type here, which is this type here. So it looks like it's a syscall. Our limit type t is a syscall. Syscall ulong type. Is it unsigned long int? So we can just use the rlimit t. I think that's appropriate here. So we're going to say rlimit t, or sorry, rlim t, and we'll say we'll call this max fds is equal to 0. We'll just 0 initialize that. Actually, you know what? Let's not 0 initialize that. Okay. And then over here, we're going to do our sign here. Yeah. So here we say max fds is equal to that. And then we're also going to take this and say size of, and then this is going to be a struct rec record, and then that's going to give us back a ptr, which we can then say we're going to call this a void star, because calc gives back a void star. So we're going to then test its return value. So we say return a pointer to allocate memory. On error, these functions return null and set error no. So we say if ptr is equal to null, then we're going to p error our call to calc, and then we're going to exit, and we're going to be able to exit failure. And then down here, we can now assign in to records the value of ptr, but we're going to cast this to a struct record pointer. Sorry, this is just called records. There we go. Incompatible pointer type struct record pointer. Huh? Struct record. Struct rec. Oh, I typoed this. There we go. Okay, so now we have our memory. This is all to initialize the global memory for storing all these records. So I can delete this to do now because we're sizing it based on ulimit. I'm going to delete this to do because it's no longer based on echo. I'm going to delete that as well. So those to-dos are gone. All of this stuff is kind of like header file stuff for the struct definitions, the records in it. I feel like some of this we can like kind of like pull out into a library of its own. But for now, I'll leave it in here. This is a to-do that I need to handle at some point. Okay. So you malloc up. Yep. So I was just giving it a read over. Okay. So we need to call this records init at some point. Let's see. So the except loop would be a good place to call it, I think. Let's check our main. So except loop is down here. Our pool has already started. Ideally, we would do it up here before any of this stuff happens. So if you look at start pool, it's making a bunch of threads. The threads are running the thread worker. It has its epoll dependency. And then the workers go into an infinite loop, and they're waiting for stuff to happen. So these threads can just wait there. They're not going to do any damage, but as soon as they stop waiting and they get down to this handle event, that's where they could start doing damage if the memory is not initialized. So technically I can start the pool first or second. It doesn't matter, but just for like safety, I'm going to do the initialization here. So this record init, why doesn't it like that? Sorry, records init. So we call records init. Call to undeclared function. Oh, because I didn't put it in the header. I did some refactoring here and I didn't put it in the header. So this is going to be worker.h. So we have records init now. And then this needs to take void. Well, it doesn't need to, but the linter's going to complain if I don't. Okay, so that initializes the records. These individual record inits, I don't think I need to export. As well as handle event, to be honest. The except loop start, and I think I can get away with just this. It's basically the stuff that the main calls. So it calls records init, start pool, except loop. That's like, this is the interface that we're dealing with here. And that means that we don't need epoll anymore as a header here, which is great. Okay, so that takes care of that. I'm just going to write all and delete that buffer. And then let's go back to worker.c. Okay, so now we have this record init that we need to call. So we're going to call that down here, record init. And then we're going to give the CFD. So what this does is the initial records plural init, this allocates the global array on the heap and zero initializes the whole thing. So because this thing is zero initialized, that means that we don't have to assign 0 here anymore. But that means that all these char stars in the records are going to be null pointers. So in order to actually use this record, we need to allocate a buffer for that file descriptor. And the reason why we don't do this eagerly for all the possible file descriptors is that, we don't know if we're going to use all of these file descriptors. It could be that our server handles like 5 file descriptors and then closes. And it's like, do you really want to spend all the cost of upfront allocating all of this memory just to only use 5 file descriptors and then shut down? It's like, no, you don't want to do that. You want to lazily allocate memory as you need it and free it when you don't need it. So that's why I have this record init here. And what it does is basically we'll do that allocation. And this allocation needs to be large enough to fit the HTTP header. So we'll need to add some logic here to handle the case where if the header is too big to fit the buffer that we have, then we need to send a response down to the client and close the connection. Okay, so that handles that. And then we want to also do a record free here. So what is the work that we need to do to free? Well, we have to actually free the memory. So if we go down here, that's what we're doing, this cleanup here. So we're going to say record free here of e.data.fd. And it's going to be all of this stuff here. Actually, no, I'm not going to do the unlock because it's not really freeing. It kind of is, but it's not. So in here, I'm just going to paste these lines here, delete all this stuff. And then we can change all this eData stuff to just FD. Okay. So we zero out the N. We then free the memory. And then we zero out the buffer. So that's no longer pointing to anything valid. Cool. So we have the allocation of the memory and the deallocation of the memory as separate functions here. So we don't actually have to do the calls to malloc and free ourselves. All right. Okay. I think that's good. I'm wondering right now if I need to set this 0 here. I know I don't need to because after the calloc it's going to be set to 0. But what if we have like a dirty record from a previous connection? Well, then it would have had free called on it at some point to release it, in which case it would be zeroed out. So I think we're good on the setting of N. I just don't want us to be at some place in the buffer that we shouldn't be. Okay. So that takes care of that. That's kind of nice. The locking and unlocking, I would prefer to have as helper functions as well. So record lock e.data.fd. Actually, this will be unlock. Sorry, my bad. Unlock. So this is going to be void record unlock of int fd. And then here we do our pthread mutex unlock. We're going to just give it the fd mu, and then we test the error. If there's an error in unlocking, then we just blow up. So we need one for a try lock as well. So I'm just going to delete this stuff, but this is, instead of locking, it's going to be a try lock. And then we'll pull out this code here. And some of this we're going to want to record.trylock of e.data.fd. Some of this we're going to need to pull back into that function. So we do our try lock. This is going to be on fd instead of e.data.fd. Gives us back an error. So if the error is not equal to, or sorry, if error is not equal to 0, then we have an error. If it's one of these, then we need to clean up. So here I'm going to say if error is equal to ebusy, return ebusy. And then here, we could actually change this to be, instead of a void, let's do like a boolean. Is that how you do bools in C? How do bools as return args in C? I think there's a standard bool, right? Bool. Yeah. And then you have the bool here. Trylock FD. So return true will be that it was acquired. And return false will be that we didn't acquire it. So here we can say if not this, then go to cleanup. So you say if we are not able to acquire the lock, basically that's what that's saying, then we just clean up. Wait a minute, that doesn't make sense. If we're not able to acquire the lock because it's busy, we just want to continue. We don't want to clean up. Yeah, that's wrong there. So we're going to say return. Yeah, we'll just return. We only want to clean up when where's cleanup here? When we EOF. This is where we want to clean up, right? Yeah. Which means that we can pull this up here. And we don't want it to be a go-to, yeah. So when we hit IOEOF, that means that we're done reading. Because read, if we do man2 on read, the read system call, if we look at return value, on success, the number of bytes read is returned. 0 indicates end of file. I mean, that's as plain as it gets there. So we have our 0 returned here. That means we're at EOF. That means that we're removing the file descriptor from the epoll CTL. So you say, hey, the epoll file descriptor, we're going to remove it. If that ever fails, they're just going to blow up because that should never fail. And then we're going to free the record, and then we're going to unlock. So basically every exit path here, we need to make sure that we're unlocking after here. So I'm going to put the unlock at the end here. So if we get into this body of the, after line 88, we have the lock acquired. That means that we have to ensure that all of our exit points from this function release the lock. And the best way to do that is just to have it at the end of the thing, and then don't do any early returns or anything that would cause it to not run this code. Okay. Okay, so we're gonna do our read. We'll continue with these assumptions for now. We're gonna have to come back and fix these at some point. That the read is atomic and it that it doesn't happen. There's no partial reads. If we hit EOF, then we say, hey, we're removing, and I'm gonna add the %LD here. Oops, sorry. %LD of the pthread self here. Say that the thread is removing it from epoll FD. I'm just say it like this because I don't think we need to be more verbose. Okay. Okay, then we read everything in. Now we need to add a to do here. Parse line as file name. We need to open file name and then write file using send file. So all of this stuff here we can delete. We're never going to handle this case. It's always going to be reads, and then the writes are going to be send files. So this can just remain here. I'll give it the thread, pthread self here as well, and just so that we know which thread's doing that. %LD. All right. Cool. All right, let's start on parsing line as file name. So we want to read this slowly. What does this say? I'm trying to ingest all of this slowly. I know it's kind of a lot, especially if you're not familiar with some of this stuff. But basically, like the function that I'm working on right now is this handle event, and this thing basically is handling events from like epoll events from one of the workers. So the worker here is spinning forever. It's in an infinite loop. So this is a thread dedicated for handling work, and it's in an infinite loop. It's waiting. So the infinite loop is not a spin loop. It's not aggressively hitting the CPU. It's going to sleep until there's work to be done. If there's work to be done, it'll stay active on the CPU. But if there's no work to be done, it'll go to sleep and get pulled off the CPU. So that's what this epoll wait does. And once this thing unblocks, assuming there's no errors, if there is an error, then we just need to continue. But if there is work to be done, it goes over all the file descriptors that there's work to be done on, and this calls handle event. And it passes in the epoll file descriptor and the event itself. So now we have this tight function here. It's not super tight, but it's getting tighter. And the first thing this thing does, it says, hey, I want to have exclusive access to this file descriptor because there could be multiple workers that were notified about this event. And so I only want one thread to actually handle the work. So if multiple threads are notified, they're all going to wake up. They're all going to try to acquire this mutex for this file descriptor. So there's a mutex on every file descriptor. And it does that using try lock, which basically if all the threads tried to acquire the lock using just the lock method, if you look at man pthread lock, mutex lock. If you just did a pthread mutex lock, that will actually block. So one thread would win and continue execution. The other threads would be blocked. And we don't want that. We want the other threads to go off and do some other work. We don't want them to wait around. Because not only would it be bad for performance, but it would also be like incorrect because the work has already been performed by the thread that acquired the mutex. And so these other threads would just be waiting around for nothing because the work will have already been done by the time the lock gets released. So if you get to this point, if you get past this block here, the thread can then assume that it has exclusive access to this file descriptor and then perform the work that needs to be done. So Linux don't have the clipboard just like in Windows Control V, where you can paste the text from the history. If someone has to make that, how would that be possible? Where every time anything is copied, it gets added to the clipboard as history. There's a feature that is shipped with Omarchy. It's like a clipboard history feature. I forget the name of it, but look for Omarchy clipboard history. So it's just the super control V if you're running in Omarchy. I know you said that you're playing around with Omarchy previously, so if you're on that now, it's just super control V and it'll bring up the menu. And yeah, some people were having some issues with it, but you might want to just give that a try. Super Control V. I forget the name of it, but it seems like it might be this thing, Walker. Universal Clipboard Open, Walker Clipboard. No, that's not it. Here we go. This is Universal Clipboard though. But you can see here it's in their documentation under this Unified Clipboard article. Super Control V is the clipboard history. And I wish I knew the name of the history software that they're using, but I don't. But it just pops up like a window like this that shows your history, and then you can select what you want. All right, cool. So let's go back over here. All right, so we're in this function that is handling the events. The first thing we do is just log that we're handling the event. And then there's only one event that we're interested in. So what I'm going to do here, I kind of like this if else because it guarantees that we'll you know what I'm going to do? Instead of doing if else, I'm not a big fan of if else. I'm going to do the if up here. I'm going to say if not this, then we have an unknown event. The problem with this is that, let me delete all this stuff. We want this record unlocked to happen, so that means that we can't do an early return here, or else we won't get the... We could check for the events before we acquire the lock. That's a good idea. So then we can just do an early return. So we check the event to make sure it's an input event before we even acquire the lock. Because if it's not an input event, we don't even want to try to acquire the lock. And that way we don't have to worry about doing an early return. Because in both these situations, the lock isn't acquired. Okay, so now at this point in the function, we know that it's a read event because epoll in is a read event. So we can perform our read into our buffer. If there is an error, then we can just blow up, which is probably not a good thing because there's other errors that we need to handle. But for now, we're just going to blow up. This stupid one. Say silly. Okay. If it's end of file, that means that we are done with this connection. We can just close everything up. We might even want to close the file descriptor itself. That'd be a good idea. Close of e.data.fd. So the record free just does the garbage collection on the buffer and zeroes out some fields on the record. But then we also have this file descriptor that's technically still not officially closed on our end, even though we hit an EOF. What we need to do is once we hit an EOF, we need to explicitly close the file descriptor and say, hey, we're done with this, which actually will remove it from the epoll as well. So we don't actually need to do all of this. We can just close the file descriptor and it'll get removed. But it gets removed in like a weird way from what I remember. So I prefer to just explicitly remove it. I'm going to add a note here. Since we close the FD, we might... actually, I don't like using we. Since the FD gets closed, deleting it from the epoll FD might not be necessary. Okay. So assuming everything else happened fine, we got a positive n value. We're just going to set that here. And so now we need to parse this line as a file name. So this read could have given us a bunch of garbage. We want to read up to the point where we hit a new line character, basically. So I'm going to use AI to write this out for me because I'm kind of lazy. And I don't really want to waste time monkeying around with this. So in C, write me a function that takes a buffer and reads up to the first new line character and places a null byte at the end. And replaces the new line character with a null byte, with a /0. So effectively that will truncate that to a C null terminated string. So let's go ahead and just, I'm gonna put that up here. Oops. So we give it a buffer and its maximum length. And then this is just some error handling for if the buffer doesn't exist, then we're just gonna... Why do we need to return max length? Void, please, don't handle that. Don't handle that. We can return... Oh cool, it handled this case too, which I wasn't expecting. So we go from 0 up to the max length. I like doing ++i. It seems to be the way the cool kids do it. And we're going to say, hey, for each character in this buffer, if it's a new line character, then we're going to just convert it into a null byte and then return, which will truncate our string. If there's already a null byte, then we're just going to return early. So basically this will give us a null terminated string, which is our file name. So we're going to run that on here, terminate at new line, and then this is going to be records, oops, dot buff and dot n. Okay. Okay, so now we have our file name. So now we need to open the file. So man2 open. So we're just going to do a regular open. So you say open the path, which will be records e.data.fd.buff, and then flags will be read only, read only, rdon. I think I need the fcntl thing here, fcntl. Yeah, I need that. Where did I leave off here? Here we go. So we open with read only, and then mode. Since we're not creating, I think I can not specify that. I don't think it's required for me to specify that. I think I can just like not specify it. So let's give us back an FD. We'll call it FFD to not confuse it with other file descriptors. It's the file descriptor. Let's look at the flag. So it could be read only, write only, read write. So we want read only. We don't want any of these other flags. Async might be useful. Enable signal. No, I don't want async. Create. No. This might be good for security. In case a symlink gets added, we don't want to follow it. We want to have it limited. So let's say no follow. No block, non-block would be good. When possible, the file is open in non-blocking mode. Neither the open nor subsequent idle operations on the file descriptor, which is returned, will cause the calling process to wait. Let's look at send file, because I think I might need this for the send file operation. Man to send file. Send file copies data from one file descriptor to another. Because this copying is done within the kernel, send file is more efficient than combination of read and write, which would require transferring data to and from user space. In FD should be a file descriptor open for reading, and out FD should be a descriptor open for writing. If offset is not null, then it points to, I don't care about offset. Okay. Let's chat with AI here and say like when performing a send file, do you normally perform it in non-blocking mode? If so, and turns E again, do you just retry it? What if the file is really large and will fill buffers? blocking versus non-blocking behavior. Blocking socket. If a socket is blocking, then send file. So socket is not blocking. So I don't think the file being in blocking mode matters. If the socket is blocking, send file will copy until the entire requested byte count is sent, or block the socket send buffer fills. Usually call it once in a loop until done. This is simple but bad for scalability because one slow client can stall a thread. Exactly. Non-blocking socket, what most servers do, if the socket is non-block, send file will send as much data that the kernel can immediately push into the socket buffer, return the number of bytes sent. If the socket buffer is full, return -1 with E again, or E would block. So send file does return size t. If the transfer is successful, the number of bytes written is returned. So we do need to keep track of how many bytes are written. Note that a successful call to send file may write fewer bytes than requested. The caller should be prepared to retry the call if there were unsent bytes. See also notes. Okay, this complicates things. Yeah, I need to track the offset. It's n. Okay, so maybe I do need to specify the offset. So if offset is not null, then it points to a variable holding a file offset for which send file will start reading data from. When send file returns, this variable will be set to the offset of the byte following the last byte was. Okay, so we can just handle the offset without recording n anywhere. Yeah, that's great. If offset is not null, then send file. Wait a minute. Isn't that the same thing? If offset is not null, if offset is not null, then send file does not modify the file offset in f. Huh? If offset is not null, then it points to a variable holding a file offset from which send file will start reading data from an infd. When send file returns, this variable will be set to the offset of the byte following the last byte that was read. That's what I want. If offset is not null, which is the same thing, I think they mean to say if offset is null, then send file does not modify the file offset of infd. Oh no. If offset is not null, then send file does not modify the file offset in infd. Otherwise, the file offset is adjusted to reflect the number. Okay, so it's either you can track it as a separate variable, or you could track it as the offset within the file description. I have a question regarding the Lua programming and about of this topic. I'm trying to analyze the Windows Defender, and is there any book or way of suggesting moving forward? I'm not really familiar with Windows, to be honest. And Windows Defender, I think, is like the firewall that's on Windows, but I'm not super familiar with that, unfortunately. And you're talking about Lua programming. Lua, I actually don't have a lot of experience with either. Outside of Nginx. Nginx has like a Lua integration. I mean, there is a website, Lua Lang. Yeah, lua.org. I mean, you can use AI to generate your Lua scripts now. You don't have to actually learn the language, but this is where I would start learning about Lua if I was interested in it. Or just search for like Lua examples. Let's see if there's anything here. Yeah. So it's PIL. I don't know what PIL is. Programming in Lua. So this is like a book. I've done a tiny bit of Lua, but not enough to have any confidence in like writing it myself. A lot of people prefer it though because it's just in time compiled, so it runs really fast, and the overhead of embedding it into C programs is very low compared to something like Python or Ruby or any of the other dynamic languages. So yeah, I mean, if I was in your shoes, I would start with this book called Programming in Lua. And it seems like it's just on their website. Just at least the first edition is on the website. There's also a fourth edition, Programming in Lua, but that's like a printed book. Let's see, maybe it's available online, also available in ebook format. Okay. Fourth edition, Programming in Lua. That's one you have to buy as well. Why is this one on their website? I don't know. I can't vouch for this. Since last updated in 2020. If you look at the publication date on this one, it says 2016 for the fourth edition. So there's a good chance that this is up to date, just the website version. Newer editions. From basics to its API with C. I would be interested in reading this myself, because if I'm ever in the situation where I need to integrate a dynamically typed embedded language into a C program, knowing its API with C would be interesting to me. The book is a main source of programming patterns for Lua with numerous code examples that help the reader to make the most of Lua's flexibility and powerful mechanisms. The book is targeted at people with some programming backgrounds, but it does not assume any prior knowledge about Lua or any other scripting languages. Okay, that's pretty good. When you buy a copy of this book, you support, for the official definition of the language, see the reference manual. So they're trying to sell you on the book here, but if you just go to online version, it says first edition, but it seems like it's pretty up to date. Yeah, I mean, I was under the impression it was implemented in C for sure, but it's like Python's implemented C, Ruby is implemented C, like all these dynamically typed languages, they're all implemented in C. For the most part, obviously there's edge cases like PyPy with R Python and stuff like that, but like for the most part, most of the dynamically typed languages, their primary implementation is in C. And so when you're writing a C program that you want to embed like little like Python programs or little scripting capability, like what a lot of people will reach for is Lua, because it's easier to embed. It's a simpler language to embed, from what I understand, than Python or Ruby or JavaScript with V8. I guess V8 is C++. But yeah, from what I understand, it's a lot easier to embed. The C API, here it goes. You can call C from Lua. Cool. But yeah, I would look at that if I were you. All right. So we did our open. I'm just going to put it in note O non-block just for funsies. Okay, so we have our file descriptor. We want to test this open to make sure that it didn't error out. So we go to return. God, this is such a long man page. Return. On success, on error, it's -1. So we just say if FFD is equal to -1, then we're going to I'm going to say p error open here. And then I'm just going to write out to the client. So we'll try performing a write here. So this is going to be a write to the e.data.fd. We need the buffer. Actually, you know what? I'm just going to go to C here. Say like, hey, C code to write out a string to a file descriptor, a string literal. So I have this weird thought that now I get to understand how human languages evolves and why we have so many languages with the same, and same with computer languages. Yeah. Yeah, I mean, I guess it's like this evolutionary symbolic process that's going on in everyone's head. We're all kind of like independently creating our own language and mutating language and sharing language, which is why dialects, regional dialects developed. Same thing with programming languages. But like C in my mind is like the progenitor of all these other languages. Like so much inherits from C. It's almost like Latin. if you're analogizing it to like human language. Also, can you see this windmill dev? What do you think about it? Yeah, I'll check that out later. If you want to post that in Discord, I'll check it out later. All right, so let's do our write here. Okay, so we have our how do I want to do this? Can I do it like that? -1? I'd rather do it like this. Sterling. Yeah, let's do that. Oops. What do we want to call this? Let's call this 500. Yeah. 500 internal server. I'm just making shit up here. Sterling of response 500. We'll just say response here 500, and then I'll call that up here. We'll just have a const char star response 500 is equal to that. And I think I need a /r/n. I think you need two of them, to be honest. /r/n. Okay. So if you have an open error, this will be response 500. I need to fix this to be response 500, and then we have to input strings. string.h. All right, so we do our write. We don't really care if the write succeeds because we're just going to unlock it and move on with our day here. Okay, so otherwise we're going to do our send file here. And we're just going to say to do huge assumption that send file is atomic. So let's go here. So we're going to say int n is equal to send file. This will be e.data.fd, and then this will be ffd. Offset will be null, and I think size count can be 0. Maybe not. Is a number of bytes to copy between the file descriptors. I don't want to have to specify that. It means I have to stat the file. Okay, I need to stat the file then. Why don't we stat it? No, we'll use fstat. Yeah. Man to fstat. This guy here. So now that we have the file descriptor, we need to say fstat on it. And we need to have our stat structure, which will be struct stat stat. So we'll do that. And then this will be a reference to stat. We'll call it stat buff. I don't know why they call it stat buff. But. And then this returns integer. We'll call this error. If error is not, if error is equal to -1, I'm going to assume it's -1. I need to check that assumption though. Return. Yep. Okay. So we p error out fstat, and we can do go to unlock. We'll do our write as well. And fstat comes with sysstat. Okay. Huh. What happened there? We lost our unlock. Oh, because I forgot to put a semicolon here. Because I wasn't done with this. Okay, so now that we have our stat, we can say, hey, stat buff dot st length, I think it is, or size. Yeah, size. And then we don't really care about n other than to check for the error case. Let's see, -1. Yep. It's gonna write that out. That's fine. Go to unlock. Yeah, that's fine. All right. And send file, I guess, has its own syssend file. Okay. Well, what's going on here? Is n redefined? Yeah, n was redefined, sorry. So n was the read up there. It's going to be the send file down here. It's fine. Okay. Well, let's see if it compiles. It has some warnings. Should fix those. cd into source GitHub, and this is going to be epoll Fileserver make clean make. Wait a minute, what's going on here? Why did this guy have worker C warnings? What's going on here? Logic is only applied to the left-hand side of this bitwise operate. Oh fuck, that's a good catch. Why was that? Was that fixed automatically? Worker. Sorry, source worker C. What the hell? Yeah, here. Logic is only applied to the left hand side. Why did it give me the warning up here? But then if I make clean it and make it, it doesn't give me the warning anymore. It's bizarre. Make clean LSHLA build. There's no more build. Well, I need to fix this. So this is going to be like this. Okay. Huh. Okay. Build main local host. Okay, we got our stuff started. We go over here now. I'm just gonna do my netcat test. No such file directory. Foobar. Okay. Oh, cool. We got a panic. Null pointer passes argument 1, which is declared to never be null. How did that happen? So handle event, open, argument 1 was null. So I hit Control C, which I can see the assignment into the buffer. But what was it open? Blocked on opening. Let's see. So we hit Control C, which should have like triggered an EOF on a read. Let's go back here. So we got our 2 open failures, which we expected. It started working on FD12. It said that it's removing FD12, which is great. And then part of that, it blew up. So removing FD12. So we remove it from the epoll stuff. We then free it and close it. Oh, but we don't return here. Then we try to open it. So here we need to go to unlock. Yeah. Make. Run it again. Test foo. And then if I hit Control C here, it just removes it, which is what we want. And then since I'm running in this, I wonder if I can go todo.md. Hey, look at that. It works. So I can request readme.md, and it reads it out. I can request the .git ignore, and it reads it out. So it's at the point where it works, but it's not like fully correct. Like there's a lot of edge cases that are not being handled by my code, but at least it's doing all the basic stuff. So, okay. Let's review this diff. So the main thing here is that we switched over to send file. We did some refactoring around the records themselves. Let's say switch over to using send file. Okay. All right. So we need to make this more robust, this send file implementation. Vim to do. Add basic file reading using send. So we did this. So I'm just going to mark that as done. Make send file IO more robust in situations that have blocking. Have non-blocking reads and writes. Non-blocking partial reads and writes. Okay. So that's the immediate to do, is to make the send file IO. Actually, just make the IO in general. Make IO more robust in situations that have non-blocking or partial reads and writes. And then at some point I want to implement the HTTP1 gets, but I don't think that's like icing on the cake. Okay. Let's go ahead and just test this out again with I want to do like two separate netcats here. To do, what do you do, like readme? Oh, well, I wonder if you can do a source main.c. Source, what do I want to read out here? I'm trying to think. There's the worker.c. Bam. What I really want is to have the state of all the workers kind of like reported live. That would be pretty cool. Because right now I don't really know which workers are blocked on epoll wait, which workers are actually blocked on IO potentially. Sorry, what was that? Live means? Wonder if there's a delay on my stream. Wonder how much of a delay there is. Let me test out the delay. So I'm going to hold my hand up. See how long. 1, 2, 3. It takes about 3 seconds. Okay, that's not that bad. You said you're going to make the workers to go live. So what I want is the ability to understand if the workers are blocked on IO or blocked on epoll wait. That's kind of what I mean there. And the reason why is because I don't want the workers to spend too much time stuck in blocking IO. In fact, I want them to spend no time stuck in blocking IO. So being able to report what state they're in periodically might be useful. The problem with that is that if you just sample that, like say once a second, you're not really getting a very fine granular understanding of where the threads are spending their time. So really I need some type of profiling mechanism. And this is where I might use like a eBPF tool. I got this book, eBPF Performance Tools by Brendan and Greg, and I've used some of these tools in the past. And I kind of want to use it to figure out where these workers are. Let's see. Yeah, I mean, so if you log everything, then you're performing IO when you log. So the IO that you're performing to log itself is going to be messing up your it's going to be messing up your measurements. And the IO for logging could block, and it generates a lot of data. Either it generates a lot of data because you're sampling very frequently, in which case you have a lot of data to deal with, or it doesn't generate enough data because you're not sampling frequently enough and you miss like state transitions and stuff like that. You're going to log everything regarding the worker's behavior. Yeah, I don't think logging is going to be the right solution here. I could do that. I mean, I'm doing that already. Some of these things, like I log when the workers are started, when the main thread has a connection to handle, when the main thread's listening. Whenever there's an error, I log that out. When the worker starts working on a file descriptor. So this is FD13 down here. If I say like .gitignore to read that file, you can see like I logged that out. But I'm a big fan of like only doing a small amount of logging to get a picture of like what's going on, and then for more detailed information using the right tools. Just want to know how you're going to detect whether they're blocking or not. So every time your program or any program makes a syscall, you can use this BPF stuff to trace that syscall. And so I think I might use BPF trace to trace the syscalls themselves. So BPF trace, I don't think I have it installed. But if I just do pacman BPF trace, yeah. Okay. So now I have BPF trace. It's been a while since I used this. Let's go ahead and get the PID of our process. I'm going to do a few things here. So the first thing I'm going to do is I'm actually going to, I don't want a full screen. I'll just pull it down here. Okay. So whenever the main thread starts up, I'm going to have it report its PID. So println, or not println, fprintf standard error, and it's going to report its PID. Process started with PID %d, new line, and here get PID. What is this thing complaining about? Implicit function declaration. So I need to pull in, let me kill these things. Man to get PID. So this is in Unix standard.h. Let me just pull that in. Unix standard.h. Okay. Why is this thing? I need to do standard IO as well. Okay. Process started with PID, and then when we start a worker, there is a worker function here. Oops. Where is it? Worker. There it is. The first thing I'm going to do is have it log out and say thread started with TID. TID. Actually, this thing does that effectively. So what I could do, I think maybe if I go back to the main here, instead of doing a separate log line here, since these listen on adders log out, let's do that. Let's go to our printers. Oh no, this would be socket. Socket.c, listen on adders, this one here, and then printf, print listening, here it goes. So that would be under printers.c, print listening. Here we go. Let's do this here, where our format string will have a %LD here, and then we'll have a %LD here, and then we'll pass that in as get PID. And then this needs to have the Unix standard.h. We can go back to our main now and delete these two. So they're no longer needed. Okay, good. So get status, get diff, source, printers. So that'll log out there. I'm just trying to collect all the PIDs and the thread IDs so that I know when I'm doing my BPF tracing, what things that I'm tracing. Bro, I think you need to do some social media thing because there's no one there who do live streams like these. You know, I don't really care, to be honest. I just want to have fun and do fun things with computers and learn and grow as a, IT professional. And I appreciate that you're here hanging out with me. Like you join the streams pretty often, but like even if you weren't here, I would still be doing my thing because I just like putting stuff out there into the ether. And if people show up and they get value out of it, then like that's awesome. But I'm not in the phase where I really want to do a lot of promotion necessarily. I'm in the phase of like I want to learn shit. And I want to do cool shit. And if that, translate into something that people get value out of and they appreciate and they want to watch, then that's great. But if not, I don't really care. In fact, I was thinking about it. I was like, if people start joining the stream, I watch some of these other streamers, like it takes a lot of their attention to actually like talk to the chat, and they don't really get a lot of shit done is what I'm getting at. Like I watch these streamers and they'll be like chatting with people and they'll do a few little lines here, a few little lines there, but they're not really like super productive on stream. And I want my streams to be a vehicle for me to be actually quite productive. Because I feel like when I'm communicating with people and putting things out there, I'm more productive than if I'm just like toiling away on my own. Like a book like this, I might have them like the Linux programming interface, the book that we just read. I just disconnected my mic. The Linux program interface book that we just read. This is a book that my entire career I've wanted to read this. Not my entire career, but a good chunk of it. I would say the past decade. The past decade I've wanted to read this whole thing. And I haven't done it because I haven't had anyone to like do it with. And I feel like the live streaming, even if no one was here, because like to be frank, like a lot, I would say like 80% of the reading, like I was just like reading by myself. But the fact that I was putting it out into the world, I felt like I was more motivated to want to get through all of it. So yeah, I guess that's where I'm at with like promotion and stuff. I don't really care. I just want to learn things and do cool shit. So back to this BPF tracing stuff. So I'm logging out the PID and the thread IDs. You know, I don't even think that this is the thread ID now that I think about it. Like when I run this thing here, this is not a thread ID. It's the get self thread ID. It's the pthread thread ID, but it's not the operating system thread ID. So you can see there's a get PID, there's a get pPID, but there's a get TID. This guy here. Get thread identification, which I think is different from this here. So I'm going to go back here and just rip grep for ptrace self. I think it's not ptrace, pthread self. So these are all in worker, makes sense. Pthread self. I'm going to replace with this get TID. And then up here, this needs to come in from Unix standard, but you also need this pound define GNU source. So I'll just throw that at the top here. If I can, pound define underscore GNU source, SOURCE. Okay. Okay. So that should pull everything in. So let's go ahead and rebuild this, and okay, it's freaking out because it's a long, yeah, it makes sense. So get TID. So in our format string, we just need to remove the LD and just do a D. Because the pthread was a long. The pthread self identifier was a long, whereas the TID is just a regular integer. It's a PID-T integer. Okay, so we made it up. Let's build it. Okay, so now we got these cool little PIDs coming out of our main thread. And then each one of our threads has a thread ID. And you can see the thread IDs are very similar to the process ID. They're just the process ID plus one, because they're basically a process ID. They're just kind of like a process that has different characteristics than a traditional process. Okay, so let's go ahead and quit out of that. Now that we have that, we know our PID now, so we can copy that and grab that. And now let's look at the let's put this into a pager here. 2 and 1. All right, let's look for our PID. So -P. And then we want to look for all syscalls. Actually, you know what? Let's just ask ChatGPT here, because I'm sure it knows. What is the BPF tool that logs all syscalls for a process ID? And then we might need to install these things. I think it's under BPF tools. If we do pacman search for BPF tools, maybe it's BPF tool. Let's see. BCC examples, maybe? So BCC is the BPF compiler collection. I know that a lot of his performance tools are probably under, wait, he did a bunch that were in Python, but I think most of them are under BPF trace now. Let's see. He has one called syscount. BCC, that's a BCC. BPF trace, okay. Okay, we'll do that. Sudo bpf trace pid is this thing. And actually what we want is one of the threads themselves. We'll just choose, can I do multiple PIDs? Actually, let's do the main PID and we'll see if it picks up the threads. This is trace point syscall sysenter. And then this filters the PID here. We won't need that, so let's go ahead and copy this. Oops. Can you copy, please? Okay. And then here, I'm going to delete this PID here. So unable to attach probes if this is expected. Set the missing probes config variable to warn. Oh, that's for enter swap on. We don't care about that. Okay, so let's do our netcat now. Connection ready to handle. And then we'll do .get ignore. So it actually exited. Huh. I wonder why I exited. Readme.md. So these are all going through 6. Maybe what I'll do is copy this, kill this, go back here, replace this with 6. 4, 5, 6. See, it doesn't like that because there's no PID. Because it's a thread ID. Huh. Well, let's try doing something similar. Let's kill this. Please go away. Stop it. Oh, am I like overloading my system now? Okay. Okay, so in here, let's use our thread ID. Okay, it's not working. Let's try this one. I think mainly this is failing because I'm relying on ChatGPT, which is like giving me garbage here. Let's just search here. Brendan Greg BPF trace tools. Because he has, let me see if it's in, it has to be somewhere in this book. See if it's easy to find. Let's see. Okay, here it is. BPF tools checklist, page 79. BCC, this is using the BCC stuff though. I know he rewrote all of his BCC Python stuff into BPF trace. Install. That's for BPF trace though. Let's try just doing like epoll wait. So we do sudo bpf trace. We'll call it kret probe. And we're going to do sys epoll wait. Epoll wait star PID is our PID. Let's try that. Probe has no valid attach points. If this is expected, set the missing probe so it doesn't like the K probe. Here, let's do a -L. Okay, so these are all our trace points. Let's grep for that for epoll. And we know, just because we wrote the program, that we're using wait. So that we can say bpf trace, sudo bpf trace, give it -e, and we want this wait call and we will printf out wait so this is enter. We'll just print out this here. I think we need a new line too, yeah. Wait, new line. So this is the enter. Oh shit, it's thrashing. Okay. Well, let's limit it to our process ID. So is there a way to limit to thread? That's for thread local. PID. Okay, let's try doing this syntax here. We'll do it on here. And we'll give it this here. Oops. Okay, I have one probe attached. We'll do .get ignore here. Does not like that. Okay, we'll do a different PID. We'll say our PID is going to be, what was it, 3? Yeah, 3, 4, 5, 3. Alright, let's try it again. .get ignore. Hey, look at that. So I want to get the thread ID. Inside a BPF trace probe, how do I obtain the current thread ID? Just TID. Okay. So let's kill our tracing, and we'll do over here our %D, and then over here we'll just say TID. Okay. .get ignore. Cool. So we can see here. So 5 and 4. Here, let me clear some space here. So we have our main PID, which is the last digit is 3. And then we have 4, 5, and 6 are our threads, our worker threads. And then I have this connection to the process, which any of the threads can handle any of the read operations at any time. So I'm going to perform a read here where I say, hey, give me the .get, we do any file, readme.md. And you see what happened here is 54 was the thread that actually serviced this request. It got exclusive access. It says, hey, okay, now that I have access, I'm working on file descriptor 2. But in our tracing down here, we attached to the process and we said, hey, let's see who calls epoll wait. So 54, we expected to call epoll wait because it was unblocked. It's handling the thread. It's going to then call epoll wait to resume blocking, or to resume waiting for further IO operations. But 56 also woke up and had to go back to waiting. But 56 didn't get the lock, didn't get the mutex, so it wasn't able to do the actual work. And so it just went immediately back to wait. That's why it's above number 4, because 4 was delayed doing some work before it went back to its wait. So now that we know how to trace specific waits, I'm interested in knowing where each one of these threads is spending its time. So we know that they're spending its time in wait, because if it was blocked in on an open operation, it would not have shown that. I guess the other thing I'm kind of interested in is so this tracing shows where the last entry into the kernel occurs, but it only tracks that one syscall. So the other syscalls that we're interested in, I'm going to leave this running because I don't want to kill it. But I will kill I'll just create a new terminal here. Let's go to, because my auto jump is broken, Cypher 0 dev epoll Fileserver. So in here, worker, the syscalls that the worker is doing, actually just go to worker itself. Okay, so here's the main syscall that it's doing, which is epoll wait, and then it goes into handle event, and then it goes back to epoll wait, and then it goes to handle event. So when it's in handle event, it could be blocked in, well, I guess it's non-blocking, so it's not going to be blocked there. The main syscall here is read, and the other syscall, the other main syscall would be, I guess, open. I'm not saying that's that important. fstat, not that important. So it's send file and read. So if you go back over here, we want this trace to also trace out send file and read, and we want to do some like aggregation on the number, like compute the amount of time spent between entry and exit of all of these. Okay, so I'm gonna hand this off to ChatGPT and hopefully it can just give me the tracing stuff here. So okay, I want to record the time spent in the following syscalls for each I'll actually give it this. That command records when my threads enter epoll wait, which is helpful. However, I also want to track when they enter the read syscalls and send file syscalls. Additionally, I want to record the time spent in the in these syscalls for each thread. as a histogram or map that can be printed out when I request it from the tracing program via input or a signal, whatever is more common. Okay, let's see if ChatGPT can chew on that. Okay, okay, I think we're at the point where we need to actually formalize this as like a program instead of like running it silly like and I think it's a .bt file is how they do it. Okay, let's go under source GitHub. I moved to Claude for code. Yeah, I need to get around to doing that. ChatGPT isn't the best. Let's go to Cypher0 dev epoll Fileserver. So in here, we're going to just make a scripts folder. Scripts. I don't like the name scripts because when you try running it, you have to do /. You can't say scripts because it wants to complete into script. You have to say /scripts, but I don't know. Maybe we'll just put it under bin directory. Yeah, let's do that. Even though it's not a binary. So vim bin, we'll say trace io.bt. And we will grab this whole thing. And we'll say hashbang user bin env bpf trace. So we have our 3 syscalls that we want to trace. We have our PID. Can you parameterize the PID to a .bt file and parameter the PID? Okay, so this records the start time, and then we look for the exits, and then we correlate those with the start times. The start times are computed by the thread ID and the probe itself. And then we compute a delta in microseconds, add that to latency. Okay, I kind of like this comment here. I'm going to grab that. And we'll call this trace.io. Sudo beep. We're just going to call this trace.io. io.bt PID. And then we have a begin. Oh shit, he broke this up into a lot of different things. Send file read. Okay. Let's grab them all. So the begin says, okay, usage. I don't like that, so we'll do that. Control C to print histograms. I wonder if that also will kill the program. We'll see. All right, so epoll weight. These are separate now because the PID is parameterized. Okay, it's fine. Okay, let's go and write it out. Let's go ahead and change mod plus x that file, and then try doing sudo bin and giving it the PID. We'll give it this PID. Oops. There we go. Oops, I messed that up. Sudo bin trace that guy. Okay. Trace point not found for sys enter. So we need to do our -L again. Sudo bpf, or I think we just say bpf, well, sudo bpf trace -L. This gives you everything. -L. And regret for send file. So it's sysenter send file 64. That's the problem there. So let's go under bin here, send file 64, exit 64. Okay, the rest of it's fine. So let's rerun it. So now it doesn't like the stir argv. We'll just give this to ChatGPT because it's hallucinating shit. Alright, bin. Okay. bpf or not bpf, io trace io.bt pid, and we'll just delete all that garbage. Okay, so we got 7 probes attached because of the begin. Alright, so now we can go in here and perform some IO. Warning, can't delete map element because it does not exist. Okay, didn't expect that. So if we do like a readme.md, oh wow, this is a crazy histogram here. You just full screen it. Did it kill? Yeah, it detached as well. So these are independent threads here. So this is measuring latencies of independent syscalls. Which isn't really what we want to do. Of each syscall. However, I want to compare how much time is being spent in each syscall with each other. Like total time in wait versus total time in send file versus total time in read. Alright, so it's more like the way that it had it originally. Okay. Oh, you can send sig USR1 too, instead of Control C. That's cool. All right, so it's vim up bin this thing. Let's try the new version. All right, we'll just copy the whole thing. And we'll delete this. We'll call this trace.io. I don't like this total thing. Okay. Let's try running that. For each error. Where's the for each? Okay, down here. Yeah, we'll give this to ChatGPT, let it fix it. Older versions, BPF trace version. Dumbass. Hallucinating shit. Alright. Syscall in total time. Bin trace IO, go down here. Total time spent in syscall is microseconds. So we're just going to print out the map. All right, let's run it. Sudo on that. Inval probe type signal. Okay. I'm just gonna blow this thing away because it's optional and it's not working. What? How did it mess that up? Sam Altman said that Chinese AI models are used for AI model to train their models. I was sort of crying. All right. Why is this thing freaking out about this now? Type mismatch for equals comparison. Comparing string with int64. If it's equal to 0, then here it's saying the same thing, PID. Int32 is string. Oh, because I typed the fucking wrong thing there. Okay, there we go. All right, so now we're attached. Now let's perform like a bunch of like readme.md. Okay, it doesn't like that. Let's try it again. It might not have had the delete because it didn't have the start. Okay, it doesn't like this delete part of the probe. All right, let's hit Control C. Total time spent in read versus wait. That's a really big integer. Well, I'm going to hack on this a bit on my own. I think that ChatGPT is not helping me out here. So, tracing total system call time for PID. The first thing is that, okay, so the entry is not always going to be guaranteed to be there because we could attach the process after it's already entered. In which case, the delete's not going to work. So here we say, okay, the thread and the probe. What is n seconds in? Does n secs mean in BPF trace? Current timestamp in nanoseconds. Okay, that's all I needed. You don't need to freaking write me an essay. All right. So that's the current time step in nanoseconds, and then when we exit, we say, hey, take the current time in nanoseconds, subtract off the previously recorded time. And then that's our delta. Then we're going to add the delta to the total time for the probe. The probe itself will be exits. So that's why we see exit on all these, which is fine. And then the starts are hanging around there because these deletes failed because the starts weren't added. Can you make the program resilient to not having start entries recorded already to compute the delta, because the tracing program attached at a later time? Let's see what it spews out here. So entry is the same. Exit now has an if. So yeah, we'll do that here. Come on. So we say if These are using 2 spaces instead of 4. Oh well. The delta, the name. Oh, cool. It's doing a little nice little string replace. I'll take that. I don't know if that needs to happen in the kernel though, because this is like the part of the program that's running in the kernel, right? Okay. This will be name now instead of probe. Probe. Get out of here. Probe. Name. There we go. Yeah, I'll take the end. But this for each thing is not supported with this version. Okay. Okay, let's try that. Okay, now it's getting fancy. Okay, we'll just not do that. Probe. I don't know why ChatGPT just hallucinates so much. Okay, so now we can do our readme.md. We can do all this stuff like get ignore, and then when we control C down here, it prints out the start but not the totals. Okay, let's try it again. We'll do readme.md, readme.md, readme.md. Give it a bunch of requests here. It still only prints out starts. So it recorded the starts for epoll wait and reads. So it's recording these, but it's not fine. Oh, because the probes aren't the same. That's so annoying. The problem with this approach is that the probe names are not the same. No, I'm not gonna do this. There's gotta be like here we go. So here we record the start. This, he used the histogram thing. Done. Okay, so what we need to do here is split these out to say start TID probe would be like wait here. And we did have 3 of these. Two, 3. This will be enter read. This will be read here. This will be enter send file. It needs to be send file 64. Send file. There we go. So now we have all of our stuff recorded in a start by thread. And then we need to do the same thing here. But now we're going to say wait here. Wait. Delta total time wait. Wait. And then this will be like that. And then we need to copy this 3 times here. So here it's going to be enter read or exit read. And we'll record this as read. Read, read, read. This will be epoll. No, this will be send file 64. And we'll do this as send file. Okay. Alright, so that takes care of everyone. Okay, let's see if that works. Okay, this is on line 21. Oh, because of the print. Yeah, I got a curly brace there instead of below the PID. It's my bad. Okay. Now, let's try doing like readme.md, readme.md. Source main worker.c and .git ignore. Okay, and then when I hit Control C, okay, this is this is what I wanted. So you can now see the amount of time being spent in read, send file, and wait. So you can see all of the time pretty much is being spent in wait when you're doing I/O. And the other thing that's worth noting here, the last entry is also a wait as well, because it keeps on getting deleted out of that map, and the last entry in the map is a wait. So that tells us our current state of all the threads, and it also tells us how much time we're spending in all 3 of those different syscalls. You should claw, bro. ChatGPT is on weed like Snoop Dogg. Yeah, I mean, with any technology, I try to spend some time with it before I adopt it, and I just haven't had time to spend on Claude. I know it's freaking amazing, and all the streamers are using it, and everyone's like going crazy over it. So I just need to spend some time with it. I might do that at some point in the next week or so. It's just not like the thing that's most interesting to me right now. I know it's like crazy to say that, but All right. So this is exactly what I wanted. So I can use this program when I'm doing further testing to trace the IO to see where I'm spending time, especially under benchmarks. Okay, so I'm going to back out of that. Now that we've proven that we're spending most of our time in wait, and we're not getting any threads hung outside of wait, which this thing clearly demonstrates, I'm going to back out of that, and I'm going to quit out of our code here. Back out of that, and we don't need this anymore. At some point I want to like take this diagram and put it as part of the README once I clean it up. But for now I'm going to close out of that, and we'll kill this connection and kill this guy here. So far it's been working really good, but there's a lot of edge cases that we're not handling that I want to handle. So let's do get status here, get diff on source. So I'm going to say all of these changes were to improve instrumentation. So we're going to say get add source and bin, get status, get DC. Wait a minute, did I not do the add correctly? Okay, I didn't put a T there. Get DC. Let's modify this a little bit because it's let's make these consistent here. We'll say sudo trace. I don't like it when they scream usage at you. Usage. Sudo trace IO BT PID. Okay, now it's consistent. Okay, everything else is great. Cool. Maybe we'll space this out a little bit here. Okay. Okay, so that's our BPF trace program. Okay. We'll just say it's just call time. Okay. Cool. So let's go ahead and open up our worker. That's where we need to do our work. So here's the huge assumption stuff. So the first one is that reads are atomic. So the reads could just like abort at any point with like E again or E would block. There's no guarantee that because we're performing a read that it's gonna be available to read. Like the epoll system is more advisory and it has spurious wake-ups. So this is like a huge assumption that we're making, and it's working because our file names are like really small. Like the reads that we're performing are small. But if we have these like larger reads, like a whole HTTP header that has a really big file name, for example, or has a bunch of headers with a bunch of garbage data in it, then that read could be a partial read, or really for any reason whatsoever, the kernel could just say the read is going to block and in which case the read won't block, but we'll get back an error code E again or E would block. So we need to handle those situations. That's like a huge assumption right now. The other huge assumption is that send file is also atomic, which is totally not true. We need to record the offset. We need to have the offset recorded in our data structure. We need to be able to resume the writing end as well. So this is going to get kind of tricky. I want to tackle the read side first, get experience with like how to handle the read side. And then basically when we're in the write stage, if we have a partial write, or for whatever reason the write is blocking, then we need to transition the file descriptor back into the epoll, but transition it as to only be alerted for writes and not to be alerted for reads. In which case, this whole situation needs to be adjusted. So maybe this needs to be a handle read event. So maybe we'll have a handle event, and then we'll have a handle read event and a handle write event, just to keep the logic separate. Because I don't want to have like the reads and writes like mixed so much. Like we can perform a write as a response to a read, but if that read ends up being partial, we need to then have further read events that come in that then we resume the read, and that logic of resumption of the read, or sorry, the resumption of the write, I should say, we don't want that to be mixed with the read stuff. Same thing with the resumption of the read. So basically we're gonna have to branch this code out into two different paths: handling events for reading and handle events for writing. I think that's like the big change to the code here. And then I want to tackle the reading first, because I think it'll be a little bit more easy to approach. And once I've done that, I'll be able to do the writing side pretty easily. And then once that's done, I just need to implement the HTTP 1.1 semantics. And then it's pretty much done at that point. I'd like to get this wrapped up today. I think that's totally doable. Made a lot of progress yesterday and this morning. So, I mean, the HTTP 1.1 stuff is more just kind of like naggy stuff, like these response codes. Like C has no built-in, as far as I know, no built-in library for like handling HTTP. So I'm going to have to like hard code a lot of stuff like response codes and parsing of headers and stuff like that. So it could be that takes up like a majority of the time, but the interesting part to me is handling the partial reads and writes and the situations where you get spurious epoll events. What else we got up here to do? We also want to handle the situation where we exceed our buffer, which will be in the read path. I'm going to move this to do into here. Yeah, that's fine. And then let's do a quick rip grep for to do. Maybe we can take care of this freeing. Get adder info, man, get adder info. And then there's a free adder info. Yep, you need to call free when you're done with it. So when we get this thing back, we got listen on adders, oops, which is in, I think, socket.c. Listen on adders. So this thing will take in the different what are these socket adders? Adder infos. And listen for each of them. So basically when we're done here, so this to do is right, I need to free this thing, call free adder info and give it the res. And to keep this thing consistent, I'm going to call it free adder info. And we do this as like a single block here. And then let's go back to our socket C. Oops. Get adder info. I mean, it's not a huge memory leak because we just do this one time up front and like we never do it again. It's an O of 1 operation, but you might as well free it. So free adder info, and then here we take in the struct adder info pointer, and we call it a result, I guess. And then in here we're going to say, hey, you just call free adder info and give it result. And if we look at the prototype here, that's actually a void as well, so we don't have to worry about any returns. I just did this to make it consistent and to limit the amount of includes that we have in the main. All right, so that looks good. The other thing we need to do is put this into our header file. So socket.h is on. We need the inverse here. Yeah. There we go. And I might want to change those variable names at some point to be a little bit more appropriate, but I think it's fine for now. So vim source main. Everything looks good there. Let's look at our header files, socket.h. So set non-blocking, I don't know if we need to export that. Let's actually do a split here. And I'm going to cd over to source, GitHub, cipher0, and epoll. And ripgrep for socket.h. So it's using the main, but it's also using the worker. So let's go over to the worker. So main.c is using the get adder info for sure. It's using listen on adders. It's using the free adder info. It's not using listen and bind. It's not using set non-blocking. But there is the worker.h, or worker.c I should say. Is this guy using set non-blocking? So set non-blocking. That is being used there. So it'll pull us back up here. So that's being used. And then listen and bind. So listen and bind is not used in workers.h, and it's not used in main.c. It's only used listen and bind in the socket.c itself, so we don't need to export that. Okay, so that takes care of socket. I just want to clean up the header files here a little bit, and then I'm gonna grab some lunch. Socket, or source, sorry. So we handled socket, ripgrep for printers.h. Sorry, printers. So that's in main and socket. Printers.h. So this thing takes a socket adders, but socket.h. See, this thing has an adder info struct. Adder info sock adder. Huh. Okay. Whatever. That's fine. I'm certain that's being used in other locations for both of those. So the other one is epoll. Epoll.h. Epoll add. Epoll make. I think make should be above add. Epoll C. I think make is like the first thing you want to read in the file, right? And then reading would be like, or adding the read. So we're gonna have to have one here to do add functions for add write and del read and write. Okay. Let's grab for epoll.h. Okay, so it's mainly socket and worker that uses it. And I think both of those, yeah, it would make sense. Socket, if you look for epoll, make, yeah, it makes sense. And worker, epoll. See, this delete needs to be moved into the library there. The weight itself, I think, is fine. Yeah, epoll make here on the start pool. And then the add read. Yeah, down here. Makes sense. The last one is worker.h. I think that's only, yeah, we already went over that one. Okay. All right, let's write everything out, and we're gonna make clean, make. Looks like everything built correctly, no issues. Let's run it, bin, not bin, build, main, build, main, localhost. And then we'll do a simple test here and see that. Oops. And then what? Source worker.c. Bam. Cool. Alrighty. This log connection ready to handle. I don't like that it doesn't have a PID or a thread ID. Let's go ahead and find that. Let's do over here, just grab for anything that's F or printf. So the usage is fine. That's all that stupid stuff. Okay. No sockets were added. That's fine. Anything down here though, connection ready to handle, I feel like that needs to have it. So vim up worker.c, and then go to connection ready to handle. And here we're going to pass in, so this is the main accept loop, so we're going to say get PID here. Okay, and then where else? Usage. That already has the get PID in it. Okay. Make, run, netcat, some garbage. That's a P error, that's fine. And then readme.md, bam. And then hit Control C, removing FD. So connection ready to handle. I kind of feel like that needs to have a file descriptor too, right? Connection ready to handle. %d. And then we give it the connection FD. Yeah, that seems a little bit better. All right, let's go ahead and make, wait a minute, make clean, make foreground, vim, worker, yeah. Okay, I was just make fucking up, I guess. Let's do that, this. Okay. See, it's still not there. Connection ready to handle. How is that not there? Worker.c. Connection ready to handle. Oh. Somehow this thing got backed out. Somehow that got backed out. Okay. Now let's try it. Make. There we go. Okay. Connection ready to handle 12. And then we're working on FD12. Maybe I should say FD colon, because everything else says connection ready to handle FD. Okay, let's do that. There we go. Make. There we go. Okay, looks good. Get add source, get status, get DC. So there's just a bunch of cleanup. Minor cleanup. Cool. All right, I'm gonna take a break here and get some lunch because I'm starving. And when I get back, I'm going to start on making the reads more robust so that they can handle larger files, handling a bunch of the edge cases around like large files, getting the infrastructure set up for handling partial reads and partial writes concurrently, and being able to resume them, which require a little bit of a state being added to the record structure. And then finally adding HTTP 1.1 semantics, which we can do a really simple thing there where we just read the header in and then just parse the first line of the header for get, and any other status code we just emit like a response code that says like we don't support the status code. So yeah, getting close to finishing this project up. So I have a question in the end, what really we will get to see and what you want to add as new features, what are not in the traditional one. So the main goal here is to have a concurrent file server that can handle more than 10,000 concurrent connections. There's other projects certainly that can do this. There's things like Nginx, even Go's built-in file server could probably handle this. But this is more an exercise for me to get really familiar with these APIs and to have a very high performance server that can handle well above 10,000 concurrent connections while doing a bunch of IO. And then if you look at the README here, it says this project mainly exists for me to learn about epoll, but also serve as a baseline in performance comparisons with IOU ring. So epoll is like, it's like the best syscall for doing this non-blocking event-based IO on Linux, but it's ancient. It's ancient technology, whereas IOU ring is like the new cool high performance user space, low syscall overhead technology. And so the eventual goal is to implement the same kind of like idea, the same test project, but using IOU ring. And then we can run benchmarks against both of them and see how they fare against each other. So we were just going through how they, yeah, exactly. Like epoll is, like, we learned about it in the Linux programming interface. It's used in Go's runtime. It's netpolar. It's used like everywhere. Epoll is used everywhere, but it's like the old technology at this point. And so this project really is an exercise for me to implement a solution to the C10K problem that's it's like somewhat interesting. It has HTTP semantics. It has, you know, some interesting stuff with like file system stuff and send file. But it's a pretty, again, in the grand scheme of things, it's a pretty small project for me to exercise using these APIs and these syscalls. And the eventual goal is to have an artifact that we can benchmark in comparisons against IOU ring. And IOU ring is really, really the technology that I want to spend some time with here. So I might have mentioned it before, but basically the idea behind IOU ring is that you are performing memory operations for IO in your own address space, and then the kernel basically marks those pages as memory that's shared with the kernel, and the kernel can then perform IO operations with a little bit of coordination with the user space without you having to make syscalls for every IO operation. There are some syscalls, but they're amortized, so they're not as costly as doing something like send file or epoll or any of these other things. And the other thing is, like, you never go to sleep. With epoll, you're actually going to sleep. At some point, your process says, wake me up the next time there's IO available. Whereas with IOU ring, you're able to spin on the CPU as long as you want. You never have to call into the syscalls. From what I understand, there's like this K-thread worker that you can spin up that makes it to where you don't have to do any syscalls. So IOU ring is really the technology I want to get a lot of familiarity with, because I think moving forward, a lot of the high performance systems are going to start leveraging IOU ring. Like, I know Postgres already uses IOU ring in a few places. So I think developing a skill set with this technology would be really good for me, given that I want to work in this space a little bit more. I mean, IOU ring was developed maybe in the past decade, I would say. Whereas epoll, really the solution to the C10K problem is epoll. Like, the chronology is that the C10K problem existed up until the development of epoll, and epoll pretty much solved it. And then once epoll was adopted by a large amount of like networking servers, it was no longer a big issue. But moving forward, we want to make utilize more CPU cores. We want to have those CPU cores actually doing real work. And so spending all this time doing context switches between user space and the kernel, and also, I mean, that's the main cost, is context switching between user space and kernel, but also copying memory between user space and kernel and back. IOU ring basically eliminates all that, so you can get a lot more performance out of your systems. It's just performance and scalability. Like, there's no real urgency for projects to move over to IOU ring because epoll is such a good solution. But IOU ring is just like, it's just faster. It's more complex of a solution. You can see like I wrote this epoll server in like an afternoon yesterday, and I spent some time on it this morning. But like with IOU ring, from what I understand, it's a lot more complex. I wouldn't compare it to IPv6 versus IPv4, because the problem with a transition between IPv4 and IPv6 is that there is network effects in play. There is adoption of IPv4, and a lot of hardware and software was built around the IPv4 stack. And then when IPv6 was introduced, it wasn't backwards and forwards compatible. So you couldn't easily transition between IPv4 and IPv6. I know they've done a lot of work to like smooth the edges. It was kind of like the transition between Python 2.7 and Python 3. Like there's a lot of breaking changes between the two. And so that transition was stalled out. And IPv6 now, I mean, it's going on like basically my entire life, IPv6 has existed. Not literally, but for the most part, for the majority of my professional career, IPv6 has existed and hasn't achieved the level of adoption that you would have expected of something that was like dominant. But most companies, especially for internal networking, they still use IPv4. So I wouldn't compare it to that necessarily, because IOU ring can be a replacement for epoll, and users could be just completely unaware of it. There's no cost in transitioning between epoll and IOU ring, and if it gives the users a performance benefit for zero cost of transitioning, like of course people are going to want to do that. It's like a no-brainer. So some of the downsides of IOU ring, from what I understood recently in the past like 8 years or so that it's been worked on, is that there's been some security issues. That's been like a big issue. So companies have been hesitant to adopt it because of the security implications. Like it kind of like breaks a lot of security models that assume the syscall boundary is being respected. And so there's been a lot of work involved in like making it more secure and more compliant with a lot of the security models that exist for Linux. So there's security issues. There's been some other kind of like issues with compatibility, but from what I understand, like all those issues have been resolved. So now it's like in the sweet spot of like adoption, where people are starting to adopt it. And I think the biggest user that I've seen so far is Postgres is adopting it. So it's not that much adopted in contrast to epoll. That's why it has that much compatibility and security issues. I mean, possibly. From what I understand, the compatibility and security issues have been like largely resolved. It's not like it's been around for a while. Let's see. Yeah, so like this manual page for IOU ring was originally published in 2020. So it's been around for 6 years at least. I think it's been around even longer than that. Let's ask ChatGPT. When was IOU ring started or initially released? Like it's been in the kernel for a while now, from what I understand. Kernel 5.1, which is in May 2019. So it's been around for a while. And you can see here, it was introduced by so-and-so to provide high-performance asynchronous I/O with a ring buffer interface, reducing syscall overhead compared to traditional epoll and AIO interfaces. How do you set to just open the ChatGPT like that? It's an Omarchy thing. So you mentioned kind of like playing around with Omarchy. So Omarchy has under config, hyperland, bindings.conf. Sorry, I kind of hit enter real quick. So under this file here, is all the default key bindings. And it's just a hyperlink thing. And then if you look here, where is it? This one here. So it just launches a web app at chatgpt.com. You can change this to be whatever you want. So when I hit when I hit Super Shift A, it just opens up ChatGPT. If I do Super Alt Shift A, it does Grok. Yeah, I like it. I like having things really quick to access, so that you can bring them up and get them out of your way really quickly. So I like that that comes default with the Omarchy installation. I didn't have to set anything up for that. Cool. I'm gonna hop off for lunch. I'm starving to death. But yeah, it was nice to chat with you. I'll get back on today to finish up some of the things that I discussed. Yeah, hopefully I'll have this wrapped up today, and then tomorrow I'll probably take off tomorrow because I got some stuff I have to work on outside of streaming stuff. So I'll probably be back on tonight, and then after that Monday. Cool. All right, have a good one.